Hi, everyone. Welcome to All Space Considered. I'm Dr. David Reitzel, and All Space Considered is brought to you by Griffith Observatory, the City of Los Angeles, the Department of Recreation and Parks, and we always like to thank Griffith Observatory Foundation, our exclusive nonprofit partner. All Space Considered happens every third Thursday of each month. Well, unless it doesn't. So check our website if you're planning on coming up here, because sometimes we move it if there's a special event or something. But we're usually on the third Thursdays. Tonight is June 20th, and it is also the summer solstice. So tonight's program will be a little shorter than usual because we have to get outside to watch the sunset, believe it or not. It will set upon our sunset line off to the direction. So everybody in our audience here at Griffith Observatory, we're going to end at about 1:15 and head out and watch the sunset because today's the solstice. It falls right on this line. And it's pretty cool. You don't want to miss it. So make sure you make your plans to come to Griffith Observatory to see this if you're off in YouTube land. But tonight we have a very special guest, Dr. Sabrina Stierwalt. She is going to talk to us about her programs of observing colliding galaxies and how this changes the galaxies, how this works in the universe, and maybe even a little bit about our own galaxy having something happen to it in the future. So everybody, let's welcome Occidental Professor Sabrina Stierwalt.
Thank you. Can you hear me in the back? Yay. Okay, thanks. So I am Sabrina Stierwalt. I'm delighted to be here. It's such an honor. My slides are gone. Okay. I have loved this observatory for a long time, and so it's a real honor to be here giving a talk. And not only giving a talk, but giving a talk where my daughter gets to be here. I don't know if she's as excited to be here as I am excited to have her here because she has to listen to my lectures all the time. But thank you for being here, honey. Okay, so I want to talk to you today about what happens when galaxies collide. But before we talk about galaxy collisions, let's make sure we're all on the same page as for what a galaxy actually is. Oh, dear. Nope. Okay. Okay, so this is going to ruin the tour. So we live in a massive spiral galaxy. Now, if you attended All Space Considered last month, you know very well that a spiral galaxy is one of the ways we classify galaxies because Dr. Reitzel talked about a galaxy zoo. And so spiral galaxies are these galaxies that are disc-shaped, and they have these nice spiral arms that form lots of stars, and they have a nice ordered rotation. And so we live in this massive spiral galaxy. Just knowing that, we tend to take that information for granted, but just knowing that has taken hundreds of years because it's really hard to get an idea of what our galaxy looks like because we are inside it. So it's like trying to understand what your house looks like from sitting inside your bedroom. So how do we do that? Well, we can study how the stars move around us. We can tell that when we look in one direction towards the galactic center, there's a lot more stars there than when we look in the other direction. And we can also look at other galaxies. And we say, okay, we look at the stuff that we're made out of, what color the stuff is around us. We look at other galaxies and we say, well, that galaxy is made out of the same stuff that we're made out of, so maybe we look like that other galaxy. So what is it that our galaxy is made out of? Yes. So our galaxy is made out of three main ingredients: stars. So these are the things that we see with our eyes and in optical light. Gas and dust. So this is the sort of stuff that permeates in between the stars and what stars are ultimately formed out of. And then dark matter, this mysterious substance that we're not quite sure what it is, but we know that it has to be there based on its gravitational tug on the stuff around it. So we live in this massive spiral galaxy we call the Milky Way. Now, our Milky Way is situated in a neighborhood that we call the local group. The major players are us, the Milky Way, and then another large spiral galaxy called the Andromeda Galaxy. And there's also a third, smaller spiral galaxy called M33, but everybody else is a small, what we call dwarf galaxies, so much smaller than the Milky Way, a lot fewer stars. But let's focus for a minute on these two major players, the Milky Way and Andromeda. So unfortunately, we are not destined to be peaceful neighbors, eternal BFFs with Andromeda, because we are actually on a collision course towards each other at 250,000 miles per hour. So for context, that's more than 2,000 times as fast as the fastest fast pitch in baseball. If you were going this fast, you could make it all the way around the Earth's equator 10 times in an hour. So very, very fast. Lest you all run out of the theater now to get prepared, because this sounds very fast. It is very fast, but space is really, really big. So even though Andromeda is our nearest galaxy neighbor, our nearest spiral galaxy neighbor, it is actually still pretty far away. And so even traveling this fast, we don't expect this collision to happen for another 4 billion years. So we've got some time. But in the meantime, we can ask, what is it going to look like? What is this going to be like when it happens? And so we can look at predictions. We can make simulations to see what this might look like. We can also, again, look at other galaxies that are interacting and merging and try to learn from those systems. So let's talk about what this is going to look like when we crash into Andromeda. The first thing I need you to know about galaxy collisions is that when galaxies collide, the stars themselves do not actually collide with each other. Now, this probably sounds pretty weird. When we look at galaxies, they're full of stars. We think there are something like 200, 300 billion stars in the Milky Way. There are something like 1 trillion stars in Andromeda. So how can you crash two galaxies full of stars with each other and not have any of them collide? Well, the answer is that not only is space really, really big, space is also really, really empty. So those are your take-home points. Big, empty. That is space. So space is really, really empty, which means there's just a lot of space in between the stars. And so to try to give you a better sense of this, I put some numbers to it. So in our solar neighborhood, so that's around where we are in the galaxy, the density of stars there is 1/10 of a star per parsec cubed. So a parsec is a unit of distance that astronomers use, because if we did everything in miles or kilometers, the numbers would get really big really fast. So we use parsecs, and 1 parsec is about 19 trillion miles. So if I had a box that was 19 trillion miles by 19 trillion miles by 19 trillion miles, in our area of the galaxy, we're about halfway out of our galaxy's disk, you would need 10 of those boxes before you even got 1 star. Now, if we look towards the galactic center is a little bit more crowded. So if you have one of those parsec cubed boxes, you'd find 10 million stars in that one. So that's starting to sound like a lot of stars, but how many stars would actually fit in that box? Well, the answer is 1 times 10 to the 21 at least would fit in that box. So that means 1 and 21 zeros after it. Trillion billion stars could fit in that box, but we only get 1/10 of a star around here, or 10 million in the galactic center, the most densest part. So another way of looking at this, in case this number doesn't really speak to you, all the zeros, is that it is more likely for you to toss a coin 27 times in a row and get heads every single time. It's more likely for that to happen than for stars to collide, for 2 stars to actually make contact and collide with each other in a galaxy collision. Okay, so what does happen in a galaxy collision? Well, here's an example of a galaxy merger that's been happening for like 100 million years. That's not a lot in my world, 100 million years. So these 2 galaxies have started interacting with each other. And one of the first things that you can see is mergers will sometimes form a bridge of material between the two galaxies, because now that material is being pulled out by one of the other galaxy neighbors. So you get this nice bridge of material showing that these galaxies are interacting with each other. Another thing that sometimes happens is you get these nice tidal tails, we call them. And so we call them tidal tails because they're due to tidal forces. Not entirely different, but pretty similar to the forces that give us the tides here on Earth, because they're feeling the tug of the moon's gravitational pull. So this material from these galaxies is now entering a tidal field where it feels the gravitational pull of its own parent galaxy, but also of the other galaxy. And then combine that with the fact that they're rotating, and you tend to get this part of this material that gets splayed out in these beautiful tails. So if we let this merger progress a little bit more, you'd get something like the antennae galaxies that have been merging for 300, 400 million years. And they're called the antennae because people think that this looks like an insect head. And then if you can see, there's these nice tidal tails coming off of it. And so the antennae galaxies, what's happening here is the merger has progressed a little bit more. And all of that material, remember, there's not just stars. The stars are pretty sparse in the galaxies, but there's also this gas and dust that permeates everywhere as well. And all of that material is starting to pool together towards a central point, the center of mass of this system. And so you get this material starting to pool there. And I mentioned briefly, the way you make stars is you compress a cloud of gas. You compress it until the temperature gets hot enough, the pressure gets high enough so fusion can happen and you can light up that star. Now, as you can imagine, you have all this material from one galaxy and all this material from another galaxy, and now it's all coming together. They're pulling together in the center of the system. You start to get you get a lot of those gas clouds compressing and forming stars. So you get new stars forming. And so here, the old stars, the original galaxies, are sort of yellowish orange. Those are the two nuclei of the galaxies that started out. And then all of these nice pink dots, some of the red dots, is this new star formation that's happening in this galaxy because you've merged all these gas clouds together. Now we let this play out a little longer, all of that material starts pulling in, and it starts to look like one system. So this is a very advanced stage merger. Sometimes you can tell that it isn't actually a single galaxy. There's some hints that it's the end of a merger. Like in this one, you can see there's sort of a wisp of a tidal tail up here still. Those big, beautiful tidal tails will either fall back into the galaxy if the gravitational pull is strong enough, but some of them might dissolve and float off. And so we start to get things that look like one system, though. You can get very powerful starbursts. So a starburst is something like at least 10 times the amount of star formation we expect, because all of this material has been pooled in the center of this merger. And the consequence of that is that eventually you run out of fuel for star formation. So these young stars, the youngest, hottest stars, they like to burn through their fuel really fast. And so eventually you'll use up all that material, all that gas and dust that you've collected, and you are left with something that looks like this. So this is an elliptical galaxy, we call it. Perhaps obviously why we call it an elliptical galaxy. Another classification that Dr. Reitzel talked about for Galaxy Zoo last month. And so these systems are basically systems where you've burned through all that fuel for star formation. You're left with basically an aging stellar population. No more new stars are being formed. And also remember, we started out with these rotating disks, right? Nice ordered rotation. And now they've come together into an elliptical galaxy that has very disordered orbits. All the stars are kind of going about every which way. And so this process is called violent relaxation, which reminds me of vacationing with small children. Violent relaxation. Okay, so let's put all this together and see what this looks like. So here's a simulation that astronomers have made specifically about the Milky Way and Andromeda. So let's look at not just what we think happens when two spiral galaxies collide, but let's look specifically at how big is the Milky Way, how big is Andromeda, what angle are they coming in at towards each other, how fast are they going? And so this simulation shows what we think this merger is going to look like for us. So here's the Milky Way, nice ordered rotating disk. We're going to zoom out a little bit so that we can see Andromeda. There's also M33 that I mentioned, which is mostly going to hang out on the outskirts and hope not to get involved. And so then you're going to see them come together and start to feel the gravitational influence of the other galaxy. And they're going to make a first pass where they get close and those tides get really strong. And so you get your nice tidal tails sort of flung out. And then they'll separate, but eventually, sort of like a slingshot, but then they'll separate and come back together because their gravitational pull will ultimately pull them back together. And then you get this ultimate coalescing in one system. So a century ago, we didn't even know that Andromeda was a separate galaxy. Right? We were just figuring out that these fuzzy things in the sky were not clouds, but they were entirely separate galaxies. And a decade or so ago, before this work was done, we knew that we were headed towards each other, but we didn't know if we would miss each other or if we would just nick each other. Now we know because astronomers have done very detailed observations of the motions of the stars in Andromeda. We know that they're headed for this head-on collision with each other. So astronomers, because we love our simulations, they've also simulated what the night sky will look like while this is happening. So this is what it looks like now, not from Los Angeles, because we have all of our wonderful neighbors and we all emit a lot of light. Well, we shine a lot of lights. But if we had clear skies, moonless nights, and maybe some powerful eyes, this is what we would see. So the Milky Way looks like a band to us because imagine the Milky Way is like a Frisbee and you're sitting halfway out in the Frisbee. And so what that looks like to us is a band across the sky. I have some Frisbee players in the audience. And here is Andromeda. So you can see Andromeda. The best time in the northern hemisphere, no moon, fall. So like October to December, you can see Andromeda. Dr. Reitzel's nodding, so confirmed. And so this is what our night sky should look like right now. Let's fast forward about 2 billion years. Andromeda's getting closer. It looks a lot bigger. We can see it. We can see it better, taking up more of our sky. It's going to be wild. So it gets better. So 3.75 billion years, if you can see the time stamp in the corner, Andromeda's real close. Things are about to go down. And so then, fast forward a little bit, remember all that star formation that's going to happen because we have all these colliding gas clouds. So we'll have a lot of star formation, new stars formed in our night sky. And then in about 4 billion years, I will return to this later, but we are likely going to be much further out. And so we will be able to see that these are the two nuclei of the galaxies. They're very warped now. They're very much feeling each other's gravitational pull, and they are definitely interacting. So eventually, the two nuclei, they'll still be separate, but they'll be starting to come together, right? So you can still see there's distinct nuclei in the sky. And then 6-7 billion years, they will have merged together. This will dominate the night sky, this merged nucleus of of the Milky Way and the Andromeda galaxy. So there will no longer be Milky Way and Andromeda. It will be what will our couple name be? Milkomeda. The Milkomeda. We need to workshop that a little bit. So this is what we think it will look like in the night sky if we are around in 7 billion years to see it. But one thing we haven't talked about at all yet is the fact that both of these galaxies have supermassive black holes in their centers. So let's go back to this picture. So these dark lines here are dust lanes, and they're hiding from view what is going on exactly in the nucleus of this galaxy. So black holes are, I could talk to you for another hour about black holes. Black holes are extremely compact regions of space where the universe has crammed so much mass into such a small volume that the gravitational pull is so strong that not even light, the fastest thing there is, can escape that gravitational pull. That's why we call it a black hole. So when you hear compact, right, black holes are very compact objects, lots of mass in a small space. When you hear that compact, it means that you need high resolution, you need fine detail to be able to see what's going on around this black hole. So we have roughly the resolution that we need in optical data. So this is an optical image, but as you can see, these dust lanes are blocking our view. So it's sort of like if you're trying to look out a dirty window, it's going to be harder to see what's on the other side of that window if you've got dust in the way. So we have the resolution that we need in the optical, but we can't see through the dust. What we need is to be able to look in the infrared. So infrared light is longer wavelengths than optical light. We don't see it with our eyes, but we can build telescopes that can see it. The problem is with infrared light, the longer wavelengths you go to, the harder it is to get that fine detail, that high resolution. There's something talking to my ear. So the harder it is to get that resolution. So we have two choices. We have the optical, which has the resolution we need to be able to see what's going on around the black hole, but our view is blocked by this dust. Or we can look in the infrared, but we have sort of a blurrier view of what's going on, but the infrared light can make its way out of that dust so we can see what's behind the dust. The dust itself also glows in the infrared, and so it tells us what that dust is made of and what that dust is doing. So here's a picture this is the best picture we had of this galaxy in the infrared until a few years ago. And so you can see it still very nicely delineates the fact that there are two separate nuclei here, which isn't as obvious in the optical image. So you can see that there's two sources that are producing a lot of energy here. Maybe it's a powerful, one of those starbursts that we talked about, those central starbursts. Maybe it's a feeding supermassive black hole. So we know that when black holes, to grow, black holes need to feed, and they feed on the gas and dust around them, and that produces a lot of energy that then will heat that gas and dust around it. So this is what our image looked like for this galaxy until a few years ago with the launch of JWST. And so I am part of a group led by someone in this audience, looking at these merging galaxies with JWST to try to understand better what is going on in the cores where you have these two supermassive black holes that are about to merge, you have powerful starbursts, you have material surrounding the black hole that's getting heated by the black hole, and the energetics around it. So we have some ideas about, we think that when black holes produce these large amounts of energy, that will go out. Sometimes it can heat gas in the form of shock waves, and that can even suppress future star formation from happening because you make that gas too hot, now it can't form the stars. So, but we haven't been able to observe this with the resolution that we need, with the detail that we need to be able to really tell if that's what's going on. And so here is our Spitzer image, and I will show you JWST. So JWST, infrared, just like Spitzer, but now it has much higher resolution and something like 50 to 100 times the sensitivity, which means we can see things that are even fainter. And so here's what it looks like with JWST. Pretty cool, huh? So you can still see two nuclei. You can see nice spiral arms still here as this thing is pulling in all of this material from this galaxy merger. So really, really incredible. Because that was so cool, I will show you one more. So this is a Spitzer image of a galaxy that this looks like one spot, right? One system, but still this image tells us there's something special going on here. This image tells us something important. This galaxy is emitting huge amounts of light in the infrared, which means something special is going on there. Maybe there's a powerful nuclear starburst. Maybe it's this feeding supermassive black hole. And so here's what that image looks like with JWST. So now you can start to see structure and actual we take multiple images like this so you can see different types of dust, different molecules, and see which ones survive near the black hole, which don't. And this tells us a lot about the interplay between the black hole, the starbursts, all that material that gets thrown into the middle of this galaxy merger. And it's not just black holes, even though they are pretty awesome, that JWST can show us. This is an example of another merger. So this merger has a galaxy this is an optical image. So it has one that has a lot more optical light than the other, and the other is brighter in the infrared. But this particular system is at an earlier stage, right? You can still see there's two separate galaxies. And in this system, it's still at that stage where it's forming lots of new stars. And so here's a look at what it looks like with JWST. And so one of the cool things about this system is that we said these stars form when a gas cloud collapses. And that means the very early stages of star formation, that baby star is still in that cloud of gas and dust that it formed out of. And so we don't have a good idea of how those baby stars, what those baby stars are doing, what they look like. And so with JWST, because we're looking in the infrared and we can see through that envelope of dust, we can tell what's going on in these very early stages of star formation that we weren't able to see before because we didn't have the resolution we needed at these wavelengths to be able to do it. Okay, so let's step back to the Milky Way and Andromeda. What does this collision mean for us? So I mentioned we might be on a much higher orbit. So these supermassive black holes are sending out a lot of energy into the galaxies around them, which gives those stars much higher energies. So these stars are going to start moving faster. They're going to move out to higher orbits. And so what they think will happen in these simulations to our solar system is that our solar system remains intact. We're not going to get destroyed, but we will be flung out to a much larger orbit, these orbits that go far from our Milkomeda and then closer in. And so our solar system should be okay, but we are going to go on a wild ride together when this happens. But you don't have to wait 4 billion years for a galaxy collision to happen with the Milky Way, because one is actually happening right now. The only thing is the other guy is much smaller. It's a dwarf galaxy. And so we are basically cannibalizing this other galaxy. And so we know this because astronomers have seen big streams, a big stream that if you simulate and sort of rewind time, it all comes back together into a dwarf galaxy. So we call this the Sagittarius stream. And so we believe that one of these small galaxies, one of these dwarf galaxies, got a little bit too close and is now being eaten up, torn up by the Milky Way. And we see streams like this around other galaxies too. Remember, we like to learn about our own galaxy by looking at other galaxies. And so here's an example. I don't know if you can see this nice stream around it of a much smaller galaxy that is being torn up. So how do we know any of this, right? I've just told you a story about what's going to happen, but how do we know any of this? And the answer is we have two approaches in astronomy. One is observations, and so these timescales for these mergers, as we saw, are billions of years. And so we're not watching them happen, right? We're just seeing snapshots, like I've shown you, of different mergers at different times and trying to put them together like a puzzle piece to see which might have come first, what comes at the end, which is not as simple as it sounds, right? So we are putting together these pieces from our observations, but we also use simulations. So astronomy is a field where theory and simulations and observations go hand in hand. I'm an observer. I like to use telescopes and take data and make conclusions about that data. But I always look to the simulations to see if they can help me explain what I'm seeing. And simulators look to my observations to say, am I getting this right? My favorite thing to do is tell the theorists that they're wrong with their simulations and that they have to do it again. So we work hand in hand in astronomy all the time. And so to give you an example of that, this is one of my favorite videos of a galaxy merger. So what you're going to see, what you're going to see is two galaxies. So this is a simulation of two spiral galaxies merging, but every now and then the simulation is going to pause and overlay an actual image from the Hubble Space Telescope. And then it's going to start going again. And you see that simulations do an excellent job at reproducing the actual galaxy mergers that we see. So another thing you might notice is that perspective is important too, right? When we see things on the sky, we're sort of seeing a 2D picture, but this will look different depending on what angle you're viewing the merger from. So this simulation has big, beautiful tidal tails. And so then when it pauses, you can see galaxies that look just like, well, you got to move around and view it from a different perspective. And so when we're taking these snapshots, not only are we trying to put them together in time, but we're also trying to figure out, does this system look the same as this system? I'm just viewing it from underneath or over on the side. And are they actually similar systems? That adds to the complications. I could keep watching it. It's so peaceful. Okay. So my last slide is what is next for merging galaxies. So I mentioned that JWST is going to tell us a lot about what the stars and the black holes are doing in this central region of these mergers that until now has been mostly enshrouded by dust and hard to see what's going on because we didn't have the resolution. We also have two major big survey telescopes coming online very soon. So we have the Vera Rubin Observatory on the ground, that's the one on the top, and then the Nancy Grace Roman Space Telescope, which will be in space. And both of them are going to do big surveys. And so what a survey means is we're going to find lots of cool stuff, right? Because we're going to be surveying big areas of the sky. And so then we can go back and find cool mergers, maybe examples that we hadn't seen anything like it before. And then we can go back with telescopes like HST, Hubble, JWST, and try to figure out study it in more detail. Also, something that my research focuses on, which again I could talk another hour about, is we're starting to, because we have these telescopes that have such great resolution, we're starting to ask, what happens when those dwarf galaxies collide? So remember, around the Milky Way, there are 50 or some dwarf galaxies. Many of those merge together in order to give us the Milky Way, but we don't understand a lot about that process when dwarf galaxies merge together. Physics is still the same, but because they're so chaotic and messy to start with, they don't have this nice ordered rotation that the spiral galaxies do. It's a little bit more complicated into what happens, and what our research is finding is that they look very different. And then finally, if you want to see more really gorgeous JWST images of merging galaxies, please check out the GOALS project, which is taking lots of images, spectroscopy of these merging systems. Thank you.
Well, thank you so much for that. We do have some time for questions. I'm going to start with a question of my own. Is there a chance that our own solar system could get completely flung out when the two galaxies collide, or are we pretty safe?
Yes, we could.
So we could,
yes.
Yeah. That's what I thought. But on the bright side, our sun will already be a red giant by then, and the
We
Earth
got
will
bigger
probably be
problems.
incinerated.
Correct.
So yeah, so we have bigger problems. But there is a chance, because there are some stars that are flying freely in between galaxies.
Yes.
Are these collisions how they get there?
We think so, because it's hard to explain. To get a star, you have to have very high temperature and pressure, and it's hard to explain that without that having been hosted by a galaxy. So we call those rogue stars.
Rogue stars. Well, maybe we'll end up as a rogue. That sounds kind of fun. So are there some questions in the audience? Yeah, let's start here.
Just to understand the scale of how big galaxies are, if the biggest galaxy we know of is a size 10 and the smallest classifiable dwarf galaxy is a 1, how big is the Milky Way and how big is Andromeda?
All right, I'll repeat this because we have some folks watching on YouTube and often they can't hear our crowd. So the question was, to identify the scale of galaxies, if the biggest galaxy is a 10 and the smallest galaxy is a 1, where do the Milky Way and Andromeda fall into that?
So if the biggest, the elliptical galaxies tend to be some of the biggest galaxies we know, which makes sense because you put 2 galaxies in to make that one, right? And so elliptical galaxies tend to be the biggest. Andromeda is like the next step down. I would say it's the biggest, one of the biggest spirals. And then the Milky Way is another step down from that, not too far. And then dwarf galaxies. So dwarf galaxies can have as few as 10,000 stars in them. 1,000 stars, some people have found, whereas our Milky Way has 200 billion stars. So dwarf galaxies are pretty tiny. And so we're sort of on the high side of average, I guess.
Yeah, I think you need more than 10 numerals to really do it right, because there are elliptical galaxies that are 10 times bigger than the Milky Way. So the galaxies come in really, really big sizes. But great question. Yeah.
Galaxy is Andromeda and Milky Way, right? And then within is solar systems.
Yes.
And so there can be numerous solar systems per galaxy.
Yes.
And as far as the black holes, are those always at the center of the galaxy?
Yes. So.
Yeah,
well, repeat it?
Yeah, go ahead and
That's a
repeat
great
it for
question. Okay, so the question is solar systems, galaxies, black holes, what's the hierarchy here? So our Milky Way, so our sun, let's start there. Very special to us, right? It is pretty average, and it is only one of 200 billion stars in our Milky Way galaxy. And then every big galaxy that we look in has something called a supermassive black hole in the center, which is 1,000,000 times the mass of our sun. So 1,000,000 stars worth of mass in this supermassive black hole. There are also something called stellar mass black holes, which form when big stars die. And so those are sort of speckled throughout, because as big stars in our galaxy die, they can sometimes turn into these stellar mass black holes. So like 1 to 10 times the mass of our sun. But supermassive black holes always live at the center, and they're sort of the kingpin of all the rotation around them.
Yeah. And the scales are very different. Solar systems are very small. Galaxies are huge. And there's billions of them.
There's a purpose to, besides of course, for life, but the galaxies have a purpose. I mean, the black holes have a purpose.
The question was whether the black holes have a purpose or not. So
that's a great question. One of the things we don't actually understand very well how supermassive black holes form. That's a very active area of research. And another question that goes along with that is that we do know that the mass of the bulge, so all that stuff in the center of the galaxy, traces the mass of the central supermassive black hole. So if you were to plot mass of the bulge of the galaxy versus the mass of the supermassive black hole in the middle, they track. Bigger goes with bigger, smaller goes with smaller. And so what that means to us is that they must be doing some sort of evolving together, but we don't fully understand why. And so that's another thing we're really trying to figure out. Yeah.
So let's go here in the front, and then we'll move back over that direction.
What If the small one collides with us while we're colliding?
So the question was, what if a small galaxy collides with Milkomedia as they're colliding?
So if a small galaxy collides with us while we're already busy colliding, it will likely get very ripped apart. And so now it's got two galaxies competing for its material. And so I don't know that you'd see that nice, clear stream anymore. You might see something that's a lot messier.
Yeah.
It's very hard to get simulators to simulate 3 galaxies. They don't like to do it because it's too complicated. There's too many initial conditions that you have to put in when there's 3. It's hard enough to do 2. Like, how are they angled near each other? So we'd have to get a simulator to know for sure, but it'll be hard.
We'll get one on the phone.
Sure.
Yeah. Is anyone over in here? Yeah, back over there.
So we know that space is ever expanding, right? So would that play into Milky Way and Andromeda actually trying to come towards one another, or is there a chance that we might actually not collide because, if it's expanding, it goes away from each other?
Yeah, the question was, due to the expansion of the universe, will that be able to pull the Milky Way and Andromeda apart before we collide?
Yeah, that's a great question. So the expansion of the universe, most galaxies we see are moving away from us, right? Because the universe is expanding. It happens that Andromeda is close enough that our gravitational pull on each other is stronger than the pull of the outward of the expansion of the universe. But that only happens when you are close enough. And so actually in the early universe, when the universe was younger, before it had expanded so much, there was a lot more, we think, mergers and collisions because everything was closer together. And now as the universe expands outward, collisions are getting rarer because everything is moving apart before it is close enough to come together.
Yeah. Yeah, here in the center, and then we'll go into the corner for our last questions. But yeah.
So once the Milky Way and Andromeda collide, will we still be able to see the moon in the sky?
Yeah, the question was, is once the Milky Way and Andromeda collide, will we be able to see our moon in the sky?
That's a great question. So the moon will still be there, but the light will be so dominant from that nuclear. I think we'll still be able to see it, but it's not a trivial question.
Yeah,
that's a good question.
That's a good question.
Because the moon is so bright in our sky and it's so close, I think we'll still be able to see it. I don't think they've put the moon in the simulation, so it's a good question.
Yeah.
But it will be trickier because we'll have that bright nucleus dominating the sky as well. So it won't be as easy.
Yeah, we probably have time for a couple of more questions. So here, and then we'll go back. Yeah, you, and then behind you. So.
What's the biggest galaxy we know of, and what type is it, and how big is it compared to ours?
Do you want to repeat the question?
The question is what is the largest galaxy we know of, and what type is it, and how does it compare to ours?
I think the biggest galaxies we know of are ellipticals, and there's something like 10 to the 13 times the mass of the sun. And our galaxy is something like 10 to the 11.
Yeah.
Well,
Depends if you're counting just stars.
I guess it depends if you're, yeah, that's true.
It's complicated.
It depends if you're counting just stars or if you're counting the dark matter
Yeah.
as well. So a couple of orders of magnitude less than the biggest is our galaxy.
Yeah, it's complicated because we find these in the center of clusters. And
Elliptical
the
galaxies.
elliptical
Yeah.
galaxies, the big ellipticals, are found in the center of clusters, and they're far away. Getting the distances to them is complicated, but it's a couple of orders of magnitude. So
It's also very hard to know the mass of our own galaxy. It seems like that should be the easiest because that's where we are, but it's very hard to find the mass of our own galaxy just because, again, we're sitting inside it.
Yeah, and I don't know the name of the actual galaxy, but I think there was one more question there, and then we'll try and squeeze you here in the front, and then I think we're going to need to end for the night.
All the galaxies we're able to observe, what fraction would you say are in some state of a merger or a collision? Like, is there a big scarcity of observational data?
So the question was what fraction of galaxies are colliding?
It's small. It's
Yeah.
a few percent, I think, but that is a major guess.
Yeah, I don't know, but your guess sounds reasonable to me. For major mergers. For minor mergers, it's probably almost every galaxy is undergoing one. We see signs of those little streams pretty much in every galaxy we image deeply enough on.
And we think the Milky Way went through at least 5 major mergers already. Yeah. So over time, there are many, but at the present universe, again, because the universe is expanding, mergers are getting more rare. I think it's only like a few percent.
Yeah. All right, one last question. We'll have to keep it short because we need to get out for our sunset. So.
Quick question. When galaxies collide, is there a nuclear reaction that has a radioactive component to it?
Question was, when the galaxies collide, do we get a nuclear reaction, like a nuclear bomb going off?
When you get new star formation, that is nuclear fusion. And so it is like a star is like a big nuclear bomb in a way, because you have hydrogen atoms fusing together and then helium atoms fusing together. And so you have these high temperatures and pressures where these atoms can overcome their repulsion, and then you get fusion. And so in a sense, all of these new stars forming are little nuclear explosions happening. Yeah.
Not radioactive like fission. Fusion doesn't produce radioactivity like that.
Right. Not like the stuff that worries us at Chernobyl. Not that sort of radioactivity. No. Yeah.
Anyway, folks, let's thank our speaker tonight again. Thank you so much for joining us. Absolutely wonderful. We'll be back. We'll be back, of course, again next month on the third Thursday, so be sure to join us. But tonight, I welcome our entire audience that's here at Griffith Observatory to head outside to the sunset lines that are up a couple of levels from us, so go up one level, and I'll be out there in just a minute to tell you what we're looking at. But once again, thank you all for joining us at All Space Considered. So All Space Considered is brought to you by the City of LA, Griffith Observatory, the Department of Recreation and Parks, and of course, we thank Griffith Observatory Foundation, our exclusive nonprofit partner. Thank you all.